Good morning and welcome to AP Statistics. Today I'm going to go over the Frappy which we had posted for homework and do a quick review of the chapter because shortly there will be a test on chapter 3. So let's take a quick look above at the Frappy. It gave you a graph which obviously has a fairly strong positive linear correlation. The first question had to do with tablespoons of sugar and freshness hours of the flour. Briefly describe the association shown in the scatter plot. Well, we just did. You could say that there is a fairly strong positive linear correlation between tablespoons of sugar and the length of time the carnations stay fresh in the water. You could also say that as more sugar is added to the water, the hours of freshness will increase. Either which way, that's really all there is to say. Part B asks you to interpret the slope of the line in the context of the study. The slope was 15.8. So, brief interpretation. For every tablespoon of sugar added to the water, we expect to see an increase in hours of freshness of 15.8. That's really all the slope says. And part C, calculate and interpret the residual for the flour that had 2 tablespoons of sugar and looked fresh for 204 hours. Well, they gave you the equation above. So plug in the number 2 for X, so you'll see what the expectation would be for hours of freshness at 2 tablespoons. The answer, 212.4. So the residual is the difference between the observation and the expectation. 204 minus 212.4 is negative 8.4. Now the interpretation. That flour that had 2 tablespoons of sugar in its water lasted for 8.4 hours less than expected. Part D, suppose we add other flours to the mix. All right, would you expect the R square for the second group to be greater than, less than, or about the same as the R square for the first? R square is the percent of variability that's explained by a linear relationship. If you throw in all these different kinds of flours, you're throwing in a whole lot of variability. Because when it was just the carnations, there is obviously a lot of control as to the length of freshness we'll see. I don't know if you ever had flowers, but carnations last a long time, whereas roses don't. And if you throw in a mixture of flowers, they don't have the same life expectancy as carnations, perhaps. We're going to see a lot of variability. Now, with that additional variability, we are going to see a strong decrease in the strength of the R and R square values. So adding in all this variability will lower the R square value that we expect to see. That's really all there was for the homework. So what do we want to do now? Well, let's just briefly review what we learned in this section, in this chapter. Quickly, there were scatter plots. Scatter plots are essentially quantitative variables on the X and the Y axis. They are coordinates we graph, and we look for trends or correlations within the data. We know how to do linear regression using the calculator now, and the linear regression model creates what we call the LSRL, the least squares regression line, which is the line of best fit that goes through the data such that it limits the collective residuals. It limits the area of the squares that can be formed from the vertical distances from the LSRL. It best fits the data. With the LSRL's equation, we also got an R and an R square value. R is called the correlation coefficient, and it shows you the strength, the form, which is usually linear, and the direction of the association. R square is called the coefficient of determination, and it tells us the percent of variability in the data that is explained by the linear relationship of X on Y. We also learned that the R value can be anything from -1 to +1, and the more close it gets to the extremes, the stronger the correlation will be. The more it gets towards 0, the weaker it becomes. R square, however, goes from 0 to 1, because you can't have a negative number once you square it, and obviously 0 means there's just wild variability that's not explained at all by the linear relationship. A perfect value of 1 would mean every last little bit of variability is accounted for by that linear relationship. We also learned that when you write the equation, you use y hat because that indicates a predictive model. We learned that when you do any of the regression, you also want to make residual plots so you can verify that the data was actually linear in the first place. Any pattern seen in a residual plot is a bad pattern and tells you that the data is not linear. We talked about the difference between interpolation, which is making a prediction using your LSRL within your domain, and extrapolation, which is making a prediction using your LSRL outside your domain. There are cautions to be found with both, but certainly much more caution to be taken with extrapolation, because once you're outside your domain, you don't really know exactly what's going to happen. And if the linear pattern that you thought was not linear from the residual plot, you won't want to make any kind of extrapolation because the pattern does not continue in any kind of linear fashion. Also, just one final note, correlation does not equal causation. So just because X and Y are correlated does not mean that X causes Y to occur. There could be lots of different variables, which we call confounding variables, that get in the way of us saying this does that. It's only through carefully controlled experimentation that we can prove cause and effect. Okay, well, on page 203 through 205, you're going to find the multiple choice portion of the practice test for the section. I've attached that to the announcement, so you'll have that there, or you can use your book, either which way. It's numbers 1 through 10 multiple choice. That's what I want you to do now. The attachment also continues on to the free response, which we're not doing today. So just worry about, for now, the multiple choice. If you have any questions, let me know. As well, ask me if you want to Google Meet, because obviously we have a new model now where we are now full distance learning. So let me know when you want help. I will be there. Have a great day.